Hey Matt, this is Dwight Souter. I hope you're doing well. So this is take two because I just recorded the trying to answer your question here previously, and found out my I had the mic turned off. So this is take two. So let's try this again. Anyway, first of all, it's very heartwarming that you are asking me for some help here, and I'm also very impressed by how much of the physics that you have retained and have used, and it's really nice to be able to see former students still doing some, at least maybe a little something with it. And I was really impressed with your spreadsheet and everything, and all the amount of work that you put into it. And yeah, there's a lot of thoughts that you have done. So that's also really impressive here too. And I think it's, if you don't mind, I think that I would like to be able to share that with my students here, and kind of showing, some of the work that you have done. And but one thing I want to address that might make your life a little bit easier is that I don't think you have to worry so much about the distribution of mass and or center of gravity at different portions of the body. You could almost treat the person as a almost like a rigid body. Now, that would matter, of how what's going on, especially if the person is in motion. But I'm kind of assuming that the person is going to be strapped to this cot, and so in many respects here, you can almost treat them as having this one center of gravity. How big they are and how tall they are and everything else really doesn't matter that much. And so let's go over a few things. So, for example, if I were to have say, a long metal bar that's uniform, you can assume all the mass to be located right here at the center of gravity, and would have, you know, so a large amount of mass and a small amount of, could be considered to be in one little tiny point. And it doesn't matter big, it doesn't matter how big or how small. If I were to take this long metal bar and put it onto its end, something like this, its center of gravity will still be at the same location, and it will still be exactly the same thing. And even if you take this metal bar and slice it up into smaller portions of it, say something like this, and let's say you slice it up something like this, then you would find this portion will have a small mass, and this would be the center of gravity of that object, and this would be the center of gravity of this object, and the center of gravity of this object, and the center of gravity of this portion of it here. And if it's when it's uniform like this, still it's acting as though all of its mass is still right there. So you can sum all those things up, and everything would be at that point. And even if you have something that's not a regular shape, so say something like a kind of like a trapezoid type shape to it here, its center of gravity would be somewhere over here, sliced up like that, or with all of its mass considered to be located at this one point right here. And if I were to take this and slice it up into smaller portions, say something like this, so you would have this. Actually, center of gravity would be a little bit more towards the end over here, but it'll be small, and this one will be off to the side a little bit, and it'll be a little bit greater, and center of gravity will be over here, and it'll be a little bit greater, and it'll be over here, and even greater. And still, its center of gravity will be acting as though if you were basically measure the torque of each one. So let's say I put this on a pivot point. Let's say I put this on the pivot point, and I take this weight times this distance right here, I would find out it has a certain amount of torque. And if I take this one, you will find out this, the one that's been sliced up, this would be having a small amount of torque, and this one have a little bit greater torque, and a little bit greater torque, and this one have a little bit greater torque. And when you add up all those torques, the torques of the one that's been segmented will be exactly the same as the one where you did not segment it. So the torques on both of these will be exactly the same. So even if you have a person, something like this, I believe like for most people, the center of gravity is close to the belly button, just a little bit below the center, a little bit below the belly button. So let's say right about here. You can assume all the mass to be located right there at that one point. And even if you take a person and slice them up, heaven forbid, but say something like this, you would find out a small amount of force over here, and the center of gravity a little bit more force over here, and a little bit more force over here, and a force over here. And again, if you kind of say you put them on a cot of some sort and measure the torque on this and all the individual torques acting over here, you'll find out the total torque of both of these will still be the same thing. So I think slicing a person up into portions and trying to find out where everything, where is the weight of each portion of the body and where the center of gravity is located really isn't all that necessary. I think you just need to find out what is the weight of the person and roughly where is their center of gravity. And so I think just treating it kind of like this might make things a little bit easier on you. All right, so now let me go back and address your other question about if you have a cot, and I'm first going to solve this as though you're not angling it at all. And so this is the part that's going to be, I guess you said it has wheels on it, you're loading up onto the helicopter, and say this is parallel to the ground, and the cot is about 76 inches long. And you said that the cot, so here's the center of gravity of the cot, weighs about 81 pounds. 81 pounds. And assuming it's in the center, so that would be at 38 inches. And let's say you have a patient who's laying down here. I'm using the X here to represent the center of gravity. And again, it doesn't matter, all the different portions of it here. Is just like the center of gravity where, the center of gravity of their entire body is located. And you said also that they're, like the average weight is about 314 pounds. 314 pounds. And let's pretend that they are 35 inches from the pivot point. And you're lifting up on this side. So I'm going to call this force Y that you're lifting up. Now, because of this, you're rotating it up in this direction here in a clockwise direction relative to the way I've just drawn out. And these two weights over here, they're trying to rotate it in a counterclockwise rotation. So for equilibrium of torques, the sum of the torque clockwise equals the sum of the torque acting counterclockwise. And so the force Y that you're lifting, lifting it at the end, so you're 76 inches from the pivot point, is equal to the 81 pounds, and at 38 inches, it makes me feel dirty saying inches and pounds. And say we got 314 pounds, and they are 35 inches from the pivot point. And so force Y, 76 inches, and the torque from the cot is exerting 3,078 pounds inch. Now, I read something when you're talking about the cot, and like the cot is like 81 pounds and 76 inches, and so you came out to be pounds per inch. So you had something like pounds per inch. And I'm not sure if you thought that was a unit of torque, and that's not. In case you were, this right here is not a unit of torque. A unit of torque is a pounds inch. So it's the pounds per inch would be if you were to, if it was a uniform shaped object, kind of like what I did up here. If it was a uniform shaped object, you just found out like for every unit of length, how many pounds it would be. That's not the same thing as what torque is. I'm not sure if you're talking about torque, trying to use it as a unit of torque or what here. So I may have been mistaken on what you're saying on there. And then the torque that the person is going to be exerting is 10,990 pounds inch. And this comes out to be a total of 14,068 pounds inch is equal to the force Y of 76 inches. And divide out the 76 inches. Inches cancel out your units. So this cancels out over there. This cancels out over here. So you have force Y is equal to 185.1 pounds. So that would be how much force that you would be exerting. 185.1 pounds of force. So if you're lifting a 314 pound person, and it's very good that you recognize that's a class 2 lever, and so the weight of the cot and the weight of the person, and because you're over a large distance, you'll be exerting 185.1 pounds. Okay. Now, the question you had about, because it's at an incline and the center of gravity would be shifting, and you are correct to some degree. So now the thing about torque. So let me zoom back into here. All right. The thing about torque is that it's, say it's force times distance, but it's actually the force that's perpendicular. And so, with all these forces up here, these are all perpendicular forces that are taking place. Now, what happens is that when it's at an angle, I don't want to zoom out too much here. All right, let me go back here. So let's say you're dealing with, let me move this out of the way here. So let's say I'm going to greatly exaggerate. So let's say, pretend that's an 8-degree angle. That's a really bad 8-degree angle. And it's relative to the horizontal. Oh, come on now. So this is pretend that's 8 degrees, all right? And this is your cot. And it's at an angle. And it is still going to be 76 inches long. All right. And you're still having to exert a force upward. Now, this part is going to be a little bit trickier. Okay. So this is going to be your force Y that you're going to be lifting, because you still have to lift the force straight up. Okay. And then the center of gravity of the cot is still going to be acting straight down. And that is, 81 pounds. I'll put this over here, 81 pounds. And the patient, say their center of gravity is right about here, and they still weigh 314 pounds. So I'm going to draw this line going down. Let's see, 314 pounds, okay? And they're at an 8-degree angle. All right, so now what you have to do is, because the torque is a perpendicular force, you have to break this down, these forces, into its X and Y components relative to the incline. So like for this 81 pounds of the cot, what I'm going to do is I'm going to draw a line that is perpendicular to the cot and a line that's going to be running parallel to the cot. And the one that we're going to be concerned about is the one that is going to be perpendicular to the cot. So this part right here is going to be a right angle. And so I'm going to call this force of the cot perpendicular. And if you look at this, we have a right angle triangle, and the 81 pounds, this part right here, that is the hypotenuse of it. The force caught parallel, this part right here, that is the adjacent side. So using SOHCAHTOA, we have the adjacent hypotenuse. So what we have to do is cosine theta is equal to adjacent over hypotenuse. So the cosine, and also this angle right here would be an 8-degree angle. So cosine, of 8 degrees is equal to the adjacent. The adjacent we don't know, so that's a force caught, that's perpendicular. And the hypotenuse is 81 pounds. Now, just a little word of caution. If you're doing this on a spreadsheet, spreadsheets like to do the calculations in radian mode. So you have to sometimes do a little extra step to convert the radian into degree mode. And if you're doing this on a calculator, you just want to make sure that you're in degree mode when you're doing this. So we need to solve for the force caught perpendicular. So force caught perpendicular, you just multiply out the 81 pounds. So you get 81 pounds times the cosine of 8 degrees. So force caught perpendicular would be equal to, let's see here, I did the work ahead of time. It comes out to be 80.2 pounds. So the cosine of 8 is, like, if I remember correctly, it's about 0.99. So 0.99, 0.98, somewhere around there. So 80.2 pounds. All right, so that would be, where's my color at? So that would be this value right here. So this, that's fine now. 80.2 pounds. Okay. Now, same thing for the patient. I need to draw a line that runs, I'm going to change colors here. Come on now. So I'm going to run a line that runs perpendicular to the surface and parallel to the incline. And I'm going to be concerned about this force right here. So this is a force of the patient perpendicular to the arm. And this is a right angle triangle. And this would also still be an 8-degree angle right here. So the 314 is the hypotenuse. The force parallel is perpendicular. So, again, cosine theta is equal to adjacent over hypotenuse. So the cosine of 8 degrees. The adjacent is the force parallel perpendicular. The hypotenuse is 314 pounds. So force perpendicular, or force of the patient perpendicular, is equal to 314 pounds times the cosine of 8 degrees. So force parallel, force patient perpendicular, try to say that fast, comes out to be 310.94 pounds. Again, I just kind of round the numbers. I'm not doing sig figs here, unless you want me to. Yeah, amazingly, students don't like significant figures here. So this is 310.94 pounds. Okay. So now, let's look at this here. So I now have my perpendicular forces of the patient and the cot. And again, this is the, what now? And This is the pivot point over here. So now we can start figuring out the torque clockwise and torque counterclockwise. All right, so, all right. So again, the sum of the torque clockwise equals the sum of the torque acting counterclockwise. And the force Y is acting clockwise. The cot and the patient are acting counterclockwise. So I'm going to say, come on now, force Y, yeah. Is it right? Yeah, okay. Let's see here. Let me just double check here. Okay, so actually, what's going to happen here is that initially when I'm solving for this, I'm actually going to be solving initially the perpendicular force. So if I take the force Y, this would be this force right here. This is my force Y perpendicular. And this is a right angle, and this would be at an 8-degree angle. Okay, so it's force Y perpendicular. So ultimately, what's going to happen here, I have to use this force Y perpendicular here. After I do that, then I can solve for the force Y. Okay, and that would be how much force that you are exerting in order to lift a patient up into the helicopter. Okay, so the force Y is equal to, you're still 76 inches from the pivot, and let's see here, it's 80.2 pounds. 80.2 pounds, and it is still going to be 38 inches from the pivot points, plus the patient at an angle, at an 8-degree angle, is going to be exerting 310.94 pounds, and they're going to be, let's pretend they're at 35 inches still. All right, so it comes out to be where torque of the cot is 3,047.6 pounds inch, plus 10,882.9 pounds inch from the patient, and it comes out to be a total of 13,930.5 pounds inch for the force Y perpendicular at 76 inches. So divide this whole thing by 76 inches. Inches cancels out. 76 inches cancels out. And so force Y perpendicular comes out to be 183.3 pounds. Okay? So that is this value over here. Okay? So let me redraw this down here. I might help things a little bit. So we got this answer over here. And kind of looking at it, I say pretend this is an 8-degree angle. And what we just figured out was perpendicular. This is 183.3 pounds. Okay, but the thing is, you're not lifting up, probably not lifting up quite like this. Instead, you're lifting straight up. So you're lifting along this line. So what you have to do is you need to draw a line that runs parallel to the incline, which would be the cot. Okay, like so here. And it would be perpendicular over here. And this would now become an 8-degree angle. I'm not sure if you can see it a little bit better over here. But this right here, so you're actually lifting up along this line right here. And this is technically, this is now the hypotenuse, and this is your adjacent. So, I know I didn't draw that quite nicely, but yeah, that's what's happening here. So you have to find out how much force. So we're looking for the force y. That's this one right here. So you're going to take cosine theta is equal to adjacent over hypotenuse again, and cosine of 8 degrees. The adjacent is 183.3 pounds, and the hypotenuse is your force y. Okay. Now, your unknown here is in a denominator, so I need to multiply that out. So force y times the cosine of 8 degrees is equal to 183.3 pounds. Divide out the cosine, come on now, cosine of 8 degrees. So force y is equal to 183.3 pounds divided by the cosine of 8 degrees. And let me just double check my math here real quick. Apologize for the delay here. I'll play some music for you. Da da do 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 do. Cosine of 8. Yep. Okay. Yep. So again, cosine of 8 degrees is about 0.99. So this comes out to be, this might shock you a little bit, 185.1 pounds. So 185.5 pounds of force is being exerted, and compare that to if when it's perpendicular, we got previously we got 185.1 pounds. It really doesn't matter. I know that may seem kind of odd here. Now, so in other words, you're still exerting the same amount of force even though you are at an 8-degree angle. Now, one thing that might help you to kind of visualize what's going on is that kind of think about, like, if you're ever lifting weights and say you're curling weights, okay, the position where it requires the most amount of effort, let's say this is your elbow and this is your forearm, and here's your hand, and you're holding onto a weight out here, which is exerting a force, and it's over a certain distance in between here. So therefore, you're going to be having a certain amount of torque, which is going to be taking place here. Okay. Now, if you take the weight and save more of an upright position, okay. So again, let's say here's a pivot point, but now your hand is almost up towards your shoulders now. So here's your fingers, here's your weight, and the weight is still going to be acting straight down. But here's the weird thing though. So the distance still remains the same. But when you break this down into its x and y components, it's relative to the arm. The force, the perpendicular force, becomes less in comparison to the actual weight that you're lifting down here. So therefore, what happens is your torque gets smaller. Whereas up here, the torque is greater. And kind of similar to that, again, let's say here's your elbow. The other position where it's going to be the easiest is when your arm is almost fully extended. And if you just slightly begin to lift up, you're going to feel a little bit. But when your arm is almost down, okay, so here's your fingers, here's the weight, it's hanging straight down. Let me make that a little bit better here. It's acting straight down. Again, the distance here is still going to be the same. You're going to have a large amount of force, but relative to the The torque arm, which would be your forearm, you're going to have a small amount of force, perpendicular force. So again, you're going to have a small torque that's going to be acting on that. So, yeah, I know that it's a little bit odd. I might be off a little bit with my rounding here, but essentially it's going to be about the same at an 8-degree angle versus if it's perpendicular to it. So hopefully this helps answer any type of questions here. It's a good problem, and it's kind of a neat thing to kind of explore what's going on. But yeah, if you have any questions or any concerns or anything of that sort, feel free to reach out to me and let me know. I enjoy doing these type of things here. So, and I just want to say that it's really an honor for you to reach out to me and ask these type of questions here. And it's heartwarming for me to hear students after so many years still have an interest in what's going on. You don't always get the outcome that you want, but still just the process of exploring and trying to figure things out, that's really something to be proud of. And so, again, I personally, I think this is kind of fun. You may not think the same way here, but, and also too, I just want to say, I really appreciate all the service that you've done, in the way that you end up serving the community. And it's really heartwarming for me to see former students who have gone off and have done some wonderful things. And it's even more heartwarming when you're finding out that they're also helping other people. So, I just want to thank you for everything that you have done. And I'm really proud of you. It's an honor for me to have had you in my class. And sometimes I use you as a kind of a bragging point here. It's like, I have a former student who, they fly a helicopter and they help other people in the process. So, that's something to, for a lot of other people to be able to look up to. So thank you. Again, if you have any questions, please let me know. I hope you and your family are doing well. If you get a chance, tell your family I said hello. And I wish your wife and your children, it's neat to see them grow up. And hopefully we'll run into each other and on good terms here. So you take care. Bye bye.